What we're going to do is we're going to look at a new way of observing reactions. Up until now, what we've done is we've looked at reaction that have proceeded in just the forward direction, where we combine our reactants, which are listed on the left-hand side of the arrow, to form our products, which are on the right side of the arrow. However, when we look at chemical systems, a lot of them don't proceed in this way, but actually establish what we call a chemical equilibrium. This is a state where both my forward reaction as written, so the things that I write on the left of the arrow become the things on the right of the arrow, but also the things on the right of the arrow, the products, become reactants. And so my reaction occurs in both a forward and reverse direction at the same time. Now, when something establishes chemical equilibrium, the rates of these two are equal. And this is a signature of chemical equilibrium, is that the rate of the forward reaction will be equal to the rate of the reverse reaction. Okay. Now, since our reaction can go in both directions, rather than using a one-way arrow that we did in the past, we use a two-way arrow. Okay. And a chemical equilibrium, for a chemical equilibrium to be established, it has to be in a closed system. So we can't have it occurring in an open system where some of my reactant or product is written in the forward direction can escape. So if I were to look at this reaction, for example, A plus B forms C plus D, I can see with my two-way arrow that it's at equilibrium. Then when I look at this, what I can see is my forward reaction is A plus B becoming C plus D. At the same time, my reverse reaction is C plus D forms A plus B. Both of these reactions are occurring at the same time. And from our previous unit, we know the rate of my forward reaction will be equal to some rate law constant times the concentration of A raised to some power times the concentration B to some power. And similarly for the reverse reaction, its rate will be equal to the some rate law constant times the concentration of C raised to some power times the concentration of D. Now the key is the rate of the forward and reverse reaction are equal. Again, we'll talk about the implications of this and how we can use this concept a little later in the unit. Now, when a system is at chemical equilibrium, and it has a number of properties that we can recognize. So, for example, we have what we call constant macroscopic properties. Now, it has to be a closed system for it to be established, but when we're talking about macroscopic properties, these are things that we can easily see or observe. So, for example, color, concentration, pH, pressure, density. Okay, and so in this vial, for example, of my copper 2 sulfate solution, the color of it is the result of the concentration of my copper 2 ions. And it has established a equilibrium with a little bit of solid copper 2 sulfate at the bottom. It's a little hard to see. And as long as the cap stays on the bottle, then what happens is that its color will stay constant. And this color is due to the concentration of the copper 2 ions, so they also stay constant. Okay, and so this is our second characteristic, is that we have constant concentrations. So if I were to take some reaction and I was to place my reactants into a vessel and seal it, and then let equilibrium be established, what I would see is my concentration of my reactions would decrease and the concentration of my products would increase until at some point when I reach my equilibrium, and then the concentrations don't change anymore because they remain constant. Also, another feature of a system that is equilibrium is the fact that it's a dynamic process. What this means is both the forward and reverse reactions are occurring at the same time. And it's constantly occurring, but they're occurring such that the concentrations of all of the entities do not change. So for example, in this simulation of nitrogen dioxide gas floating around, and we can see that by our blue spheres with two red spheres on it, they will, when they collide, if they collide with the correct orientation and sufficient energy for a reaction to occur, will then become my dinitrogen tetraoxide, which is recognized by the four 2 blue spheres attached to each other with 4 red spheres. Okay, so if we watch our simulation occur, okay, we can see our particles moving, and as they collide, we will get a reaction occurring. So far we're seeing ineffective collisions occur as they're moving around. But eventually, 2 particles will approach each other with the correct orientation, sufficient energy to react. And we'll notice that when the first 2 particles collide, they will join together, and another particle will separate. And so the number of NO2 molecules and N2O4 molecules in this vessel do not change over time. Another characteristic of our system of equilibrium is that I can establish it from either direction. So I could start off in my closed vessel with only reactants, or things that I wrote on the left-hand side of the arrow, or I could start off with only products, things that are on the right side of the arrow. And if I let equilibrium become established, it doesn't matter which direction I start off with. So here we can see for a system where I combine hydrogen gas and iodine gas to form hydrogen monoiodide, it doesn't matter whether I start off with only reactants, hydrogen and iodine, as I can see in the graph on the left, and I had no hydrogen monoiodide, or if I start off with hydrogen monoiodide and no hydrogen iodine, in both cases, I'll establish equilibrium. A final feature of systems at equilibrium is that when any system at equilibrium is established, it will respond to a stress or an external factor, for example, a temperature change, and it will respond to that stress visibly. So we'll see it in a change in their macroscopic properties. But when we remove the stress, it will return to its original position. So here we have 4 tubes containing a mixture of nitrogen dioxide and dinitrogen tetraoxide, and our NO2 is brown in color, and our N2O4 is colorless. And so if I take my tubes and I place one in a hot water bath, we can see that it's going to respond to the stress and it becomes darker, indicating that I have more NO2. And likewise, if I place the one on the right in a cold water bath, we can see that it gets clearer, indicating it has more N2O4. But if I remove the tubes from their water baths and I give them a second, they will return to their original equilibrium position, and we can see that in it returning to the same color as the reference tube that was not placed in the water bath. And it occurs for both the hot water bath and the cold water bath. Now, our equilibrium systems can be established as 2 types. We can have a homogeneous equilibrium where all of my substances in the equation are in the same state. For example, in this equilibrium where they're all gas particles, or they can be a heterogeneous equilibrium where they're in different states. And here we can establish an equilibrium between the liquid and gas form of water. Finally, when we have a system in equilibrium, we can have 2 ways of expressing how much reactant and product are present in the system. And the first one is what we call percent reaction. And this is similar to our percent yield that we did last year, where we would look at the relationship between the amount that we theoretically produce over the amount that we have. And so we can look at our concentration or amount at equilibrium over the amount all of our limiting reagent was consumed. So if we look at our different potential ranges of our percent reaction, it gives us an idea of what we would expect to have more of, or what we call position. So if I have a percent reaction of 0, no reaction occurred. Less than 50%, we say our reactions are favored. More than 50%, our products are favored. And greater than 99%, it's not a system at equilibrium, it just goes straight to product. A second method where we can express their position of equilibrium, and we're going to talk about this one in depth at a later date, is what we call our equilibrium constant. And our equilibrium constant is a relationship of the concentrations of the different entities at equilibrium. Okay, and so if this was my system at equilibrium, my equilibrium constant would be equal to the concentration of the products raised to some power over the reactants raised to some power. And we'll talk about where these different things come from. But one thing to note, solids and liquids are not included in our equilibrium constant.